大家好，我是王不老说半岛。Hi, folks. Today I'm going to continue my discussion on the packaging process technology with a focus on interposers. There are three types of interposers that we know of. There are glasses, there are silicon, and they are organic. I think we'll talk about them one by one. Today I would like to focus on glass. And I want to show you how I completely study with Perplexity AI and connected papers. In these AI days, many study can be activated, initiated with Perplexity AI and in connected papers. And they are very helpful in expanding our horizon and accelerating our studies. I would like to share with you my experiences with them. Okay, so today's the topic is glass interposers. If we look at the migration from flip chip to hybrid bonding, and here I'd like to show you this picture on the bottom left. C4, so the flip chip is 100 bombs per millimeter square, and move to micro bomb, it's about 7-8 times more, is 800. So that is the micro bomb. And then go to this SOLC, which is the famous interposers with hybrid bonding. Okay, so this is a hybrid bomb. It's a bombless. There's no bomb. Okay, there's no solar bomb here. Here is just your solar bomb. And then when you directly connect your interposers with the dies, you use hybrid bonding. You use copper to copper bonding, and as dielectric to dielectric, this kind of hybrid bonding. And there's no bond. And that you can see that the contact packing density increased dramatically to millions, up to millions, 1.2 million per millimeter square. And that is the ultimate one, which we discussed previously in a couple of talks about HBI. So before we proceed, let's look at interposers. These are our focus, right? Let's see where it sits. This is die, right? And then die is sitting on interposer, interposer sitting on SiP silicon in packaging substrate, and SiP eventually sits on the circuit board. And in between it, there are bombs. And then, of course, interposers between die could have micro bombs or bombless. This is just example. I just want to show you where the interposer sits. Okay, the purpose of interposer is to spread the connection to a wider pitch, to reroute connection to another connection with a different pitch. From a pitch perspective, from a denser one here to a less denser one, below it, beneath interposer. That's what it's trying to do. And then, of course, you have a lot of holes. That's what you do, right? You have RDL, this line is RDL line, and you have a lot of holes. So this is a hole, you put copper there, and then that's how you can talk to what you want to talk to the die next to you or to somewhere else. Then the question is, what type of material that we like to use for the interposer? That's the question, right? You could use silicon. As I mentioned before, that silicon is a natural choice because it's rigid, it's pretty good thermal conductivity, and then so you have a mechanical and thermal integrity that you like. So, and then it's reasonably cheap. Not exactly that cheap, but it's because we've been using forever, right? So you have a lot of process that related with silicon interposers, and that's why it's the most abundant usage everywhere. So anyway, but since we're doing that, let's have some fun here. Let's say study interposer material with Perplexity AI. So what I want to do is to to ask Perplexity AI a question. All right. And that question, if I click here, what are the key features? So what are the top three? Well, sorry, the top patterns, which I already show you. What are the key features? Top here. And I'm going to show you in the beginning. Please compare these three interposer materials: silicon, organic, and glass. Right. So that's a question I tap it into my Perplexity AI. This is the AI tool that I use. Perplexity AI is I think, is the best AI out there to do a scientific study. The reason is that it's better than ChatGPT uh, because it connected with Scholar AI, Google Scholar, and that make it very standing out. If you look at the format, the layout of the Perplexity AI is much nicer. So I'm asking a simple question. Please compare these three interposer materials: silicon, organic, and glass. Okay. And then this is result popped up, answer. Okay. Say silicon interposers, high performance, well, higher cost, tunable, high thermal conductivity that we know of, and then the organic, and then the glass. Okay, it leaves the bullet, and then in each bullet, it has the reference. So you click the reference, that's exactly linked to where it is. HTTP sometimes give you a funky reference that does not reflect the reality. Here it does. Here everything is real, because see, this one connected to semi engineering. This is a paper. Okay, this is Google scholastic, and then all these are real publications. So you could click to and see whether what the Perplexity AI says is true or not. So it lists out this, right? And then I say, okay, please compare a simple table to the comparison above. I'm getting lazy. I say, make a table for me. Otherwise, I have to copy and paste. That's a lot of work. I want to improve my productivity. So I said, do it. And here it is. Okay, here it is. It turns out a very nice table, generic, very nice table about comparison of these three. And I put it here. I use the Microsoft PowerPoint designer, a feature called designer, then it would automatically arrange everything for me. So it did this nice page layout for me. So this is how I have fun with Perplexity AI. And I wish you could, I would like to share with you that you could use it into your daily task in studying all the science problems. Or maybe not science. I'm just focusing on scientific papers. So I use that a lot. But let's be careful, right? It's really useful, but don't trust it 100%. You see, currently this large language model is compile everything together and try to make sense out of the information they get. So sometimes they made a mistake. Sometimes they compare apple to orange a lot. So you are sometimes confused what exactly they say. It seems on the surface they are quite reasonable, but sometimes they give you the conclusion quite inaccurate. So be careful. Don't trust them 100%. Use them to help you to search something out there which you cannot or have to spend all the time to find it. You just ask them, they will fetch for you. And always double check by going back to the original reference provided. If you have any questions about the conclusion, about the bullet that you find, always go to that real paper and study it. Okay? So now I'll go back to glass substrate. The glass substrate, it turns out cheaper. They can make it bigger. Silicone, no matter what, is still more expensive than a piece of glass, right? And in some case, you could save some money. And that's anything can save a dime, people will go for it. So in this especially because you're making millions out of it. Okay, so and he has some other features that that the vendor claim they are better. In go back to this table, silicon, organic, the three we have silicon, we have organic, and we have glass. And then of course, organic is the cheapest. Are they being used? Oh yeah, they've been used of course, and they have a lower performance. Yeah, they are lower performance, but they are cheaper. And if those concerns are not a big problem, like coefficient of thermal expansion CTE is not a big problem, then it's fine. Glass, the same thing. Glass is better than organic, but not as good as silicon. Okay. But it has own advantages. Significantly lower cost, right, compared with silicon interposer. And then they are rigid, right? So you could make holes closer to each other compared with organic. Organic kind of hard, right? And soft. So it's difficult to do some process when you're very closely packed. So that the densification and scaling a little bit harder for organic. But glass can really do it. It has its own problem, and it has other advantage. It has ultra high resistivity and then low electrical loss. This one's unique, right? Because if you have RF, you are to integrate RF to your chiplet, for example. Then using silicon, well, you have you're going to have a problem, right? The RF going to see that silicon. It's not nice because the RF can create eddy current in your silicon substrate, and now you got a signal loss. And here glass is kind of immune to that, right? It's ultra high resistivity, and then therefore no pretty low eddy current, so it will low electrical loss. So that's the built-in advantage of glass. There are other advantages, by the vendors like Prismark and all that. They have zero moisture absorption, high chemical resistance. From process perspective, things can easily absorb moistures. You have to keep it dry all the time. Silicon is the same thing. Silicon, if it's surface hydrophilic, it can quickly absorb water. That give you problems. Sometimes you want that, but sometimes you don't want that, right? And that glass, in one hand, it's zero moisture absorption. And on the other hand, it has a very high thermal chemical resistance. So you could go through a process without worrying about, suppose you have silicon, right? If you want to add something, you better not use any acid. Some acid is really harmful for silicon. But this is a piece of glass. Just don't do it with HF. Otherwise, everything else is fine. And then the CTE, the coefficient of thermal expansion is small. But it's not too far away from silicon, but it's still small. It's better than organic interposer, isn't it? So, and then it can make it thinner. Overall package can make it thinner. So the glass ball with the TGVs through glass vias compared with TSV through silicon vias. This G is glass, T is through. V just vias, just this is our vias, right? It's thermally and mechanically stable. Well, that's the advantage is low warpage. But that's, I would say, you are talking about comparison to organic. But silicon, that's not the case, right? Silicon has 2x Young's modulus. The SiO2 is about 75 gigapascal, and then silicon is 130 or higher. It depends on the phases. So you see, the silicon is better, and then the thermal conductivity is 100% better, right? This is metal, the silicon is metal, and this is insulator, so it's 100%. I mean, 100 times better. So this wording from the Prismark, I think is saying I'm compared to organic. I don't think he meant comparing to silicon. And the surface flat is very flat, right? You can make the glass very flat. So, and that could make your litho friendlier, as more friendlier, something like that. And that's good. Organic wise, it will be a little bit hard, right, to make super flat. It's a piece of plastic, right? So that's a concern. So here is the advantage of glass substrate. Then the next question is, how am I going to drill these holes? I'm going to drill these holes. Are these easy? Well, SiO2 is not a big problem, right? But this is big. The hole is large. It's not like you do IOD 0 or IOD in the back end layer, you're nanometer. So you use dry edge. And then this is 100 microns. This size, 100 micron, is still a thin one. Imagine a thick one, 1,000 micron. And you want to drill holes with a dry edge, and then you're crazy, right? I don't think it's gonna work. And so what do you do? So people already figure out this process is already called LIDE. LIDE, LIDE, laser-induced deep etching. And LIDE pretty much is common in the MEMS world. Now they improve it. This used to be doing the MEMS. And what they have in mind, like this RENA machine, is laser. They're using a laser to drill holes. You drill holes, and then after they drill holes, they etch it away, the what's left inside. What the laser does is that laser introduce a modification in glass. It weakening the glass structure in your area that you want to patch. You want to drill holes, right? You want to drill holes. And you want to drill deep. And you want exactly vertical. The alpha has to be like 0 degrees, ideally, right? You want it all the way through. And you want it crack free because imagine you're using laser to do some work, the heat going to do something, right? You must avoid this crack all over the place. If the crack, then you're gonna get problems. So they find out that if you tune the laser properly, they could get the crack free, and they could control in every hole they control. They could control all the way through or halfway through, whatever they want. And it turns out they could do the depth 200 to 100 micron, and then aspect ratio up to 10. So this is what these guys claimed. In the arena, there are a couple companies in the world that are doing this. I will introduce maybe two. And if you look at this is Vitron. Vitron process is doing the same thing. These are Vitron, and then this is RENA. Okay, RENA, and they're competing with the same thing, right? This market, and what they have is the same thing. Here's a picture a little bit clear. They use HF to wet it off. Right? They don't want to see some examples how exactly they did it, and so the overall, this is the picture that you can see. If you laser drill TGV, well, this is when a vendor come out and try to sell something, they will say, hey, look at the other guy doing this thing. They would drill a hole and then it's crack all over the place. And my laser won't do that. Retrail won't do that. Yeah, it's beautiful, no crack. And but my question is, why is tapering so large? Kind of large to me. So bear with me. Let's try to look at the advertising. It's interesting. Let's give it a couple minutes and let's see what they say. We go to this CES show. You see a bunch of advertisement. Vitron, this is their advertisement.
This has a lineup of excellent properties. It is therefore the substrate or packaging material of choice for numerous microelectronic, MEMS, microfluidic, and display applications. But glass has also a fundamental limitation. It is an amorphous material and therefore cannot be etched anisotropically. Hence, etch masks, which are typically used to create microfeatures, are underetched. These underetched areas grow at the same speed as the features grow in depth. Consequently, microfeatures created by this process are limited to aspect ratios smaller than 1. Alternative microprocessing technologies are typically associated with low throughput and insufficient quality. Especially microcracks and thermal-induced stress are major setbacks for most of these state-of-the-art processes. These problems are avoided when using laser-induced deep etching, or LIDE. LIDE is a two-step manufacturing process for particularly deep features in glass. In the first step, standard glass is modified by a pulsed laser from LPKF Laser and Electronics in a high-speed, direct write fashion. A single laser pulse is sufficient to modify a thin glass from one side to the other. Several thousands of pulses can be produced every second. Standard wet etching is the second process step in LIDE technology. The previously modified areas are preferentially etched and, if necessary, enlarged to their final size. Microfeatures created in such a way show outstanding quality. LIDE processed glasses are free of microcracks, chipping, and thermally induced stress. It comes as no surprise that LIDE processed glasses show exceptionally high break strength. LIDE technology offers infinite possibilities. The universal building block for all these possibilities is the line-shaped modification induced by a single laser pulse mentioned earlier. One detached line-shaped modification turns into a microhole. A series of these modifications along a toolpath turns into a microcut. And an array of modifications, which intentionally do not penetrate the full glass substrate, turn into a pocket. Low cost and its versatility make LIDE a new base technology for electronics, microfluidics, display, and microsystems. If you would like to take advantage of LIDE or have further questions, please contact us at.
All right, so that's what they have. I think it's a good introduction for us to learn something about. Pretty much in a detailed way, if you look at the other vendor, the Nichiwak, Japan, the laser come out, right? You could come in and modify the material inside. That's what the laser does. And what kind of laser they use? Right now, it's going to picosecond lasers, not femto. The picoseconds doing a better job these days. And they are the ultra short pulse, and they are the near infrared lasers. They go into this interior of the glass and then modify the interior. And it cuts the glass by changing the compositions. So that's what this Nichiwa company, their laser can do. So I introduced you 3 vendors doing this business. Now let's look at the connected papers. So I find out there's a paper that is investigation of low cost through glass via formation on this BSC glass, borosilicate glass by picosecond by this type of lasers. So let's look at more details. But how do I find a paper that is more details and then find out are they really important? So that's where I'd like to share with you connected papers. So when I go to connectedpapers.com, and this is what I found, and I copy this paper to it, and then see this is Connected Papers website, and then this is the paper, original paper, and immediately create a cloud of all the paper that refer to this paper, that reference to, that mention this paper, and there's a link. The size, meaning that the more mentioning, the more citing, the more important that is, right? So you could quickly browse through all these papers that are relevant to it. And here I saw a paper that interests me is reliability of copper through, right? So this paper, reliability of copper through packaging via bare glass interposers. When you deposit copper into your TGV, what happened? So that's a question, and that's what the reliability, which I'm going to talk about later in this talk. But you can see the benefit of this bubble cloud that presented here that give you many interesting paper, and it will give you a summary of this paper under it, right? So you could quickly browse through whether this paper is of interest to you. So this is the AI I'm trying to share with you, a second AI. Okay. And this paper, I find it, and then this is a paper that why it's interesting to me. It gives you a little bit more detail about forming the lasers and how does it with, interact with your glass, right? Previously, you just shown, oh, this is what you do, right? You blast a glass with some kind of frequency and some kind of depth. So what happens? So this is exactly what I'm doing. The motion of the plate moving left and right, and then these are lasers. All kind is a simple schematics of the lasers, how to manipulate the lasers, and how do you form in the tape? I'm curious about the tapering of the hole that drilled by the lasers and the subsequent wet etch process. And this paper kind of they give you explanation a little bit more detail. So idea is the same. You blast a laser, and then you etch it in HF or modify HF, like BOE or something like that. And then you have this taper, okay? And he's studying how do you control the taper angle? That's the process control I'm talking about. And this is the hole. So when you initially blast it with this, you blast the laser, and then this is what you happen. You see an irregular shape. Many things happen at the same time, and then these damaged glasses inside the hole. And then you dip in the acid, and here, and if you control it properly, it will etch only the damaged area, but not the other part. We know HF can eat up glass, right? But if you tune your chemistry properly, it will only eat up the part that has been damaged by lasers or plasma, per se. And the paper says that it's very easy to get a taper 0 degrees, exactly parallel or vertical to this plane with pure glass. But with a BSG, it's very hard. BSG or boron there. You got boron there, things got screwed up. So you got 10 degrees in general if you don't watch it. So here, if you look at it, right, you get this 10 degree easily. So the paper is trying to say how I'm going to control that. And it turns out there are many ways to control that. And you could use laser pulses, and you could change the composition of BSG, and your wet etch chemistry. This one, you etching for 20 minutes, you become this shape. If it's 10 minutes, you become that shape. So you could do a DOE pretty much to modify the angle. And so that is a little bit more detail about the LIDE process. At the end of the day, you want to control your taper less than 1 degree, which is exactly almost vertical visually. And there's nothing you can do better than that. And when you clean something up with HF, this paper, I think this most recent paper just published. And then he has the very detail about how SiO2 etch and with the BOE. So this one, I think is a good mentioning. And this one say in A2C, your equilibrium reaction with surface xenon group in etched solution with different pH value. It's a function of pH value. So when the pH value, then you will form different hydroxyls, and then you will different wet etch chemistry. At the end of the day, you want to form this, right? That's what you want to form. So forming this SIF bond, and then that's gone away. So This one, I think, is the most comprehensive silica glass wet etching mechanism that I have found as most comprehensive. And this is not the purpose of this talk about going to this mechanism. I just want to show you that this is available. If you're interested, you can find, you could go and dig a bit deeper. Here we're going to the reliability test. The reason is that, yeah, you could drill perfect holes. Then what happened afterwards? If you put copper there and then you heat it up, what happens? You may get crack-free after LIDE. Remember, in the film we just saw, it's, oh, my process is so beautiful, and I got crack-free. Let's see the crack-free. See, if we're advertising LIDE, my LIDE process make micro hole free of any surface defect. See that? Very nice. Compared with this junky, somebody else did it. I'm much better. Yeah. You're right. Yeah. Sure, when you just made, you could be crack free, right? Could be. But that's not the end of the story. The true story is that can you endure your thermocycling test? See, here people done experiments, this paper, Demir, they put copper right inside this glass. And then after some reliability tests, well, it got delamination. The copper delaminate from the glass, and you got cracks. So there you go. Cracks can exist. Yeah, it can exist after you have a perfect formation of from the LIDE process. Then if you do more, you can find then people try to do a lot of theoretical work, try to find out what is the reliability of copper through package via this TGV, and then they come up with this formula. And reliability experts are really good at this. And you can see that the number of cycle to failure can be estimated, and the strain related to that can be related. The Young's modulus, and then the tensile, the material property, the tensile strengths, all can be related to this formula and then calculated. So people, I would say the reliability picture is pretty clear. It's pretty clear. And if you want to go a little bit deeper, so this is another paper, so reliability study for large silicon interposers. They always present you with this picture. This picture is a Weibull analysis pictures. This Weibull analysis picture, and then their test. They did a test and see which one failed first, which one failed second. They have a distribution. DT is called drop test. Here, you drop it. Simply you drop it with certain height, like 1 meter, according to the spec. And then the thermocycle on board, this is probably the most important one. After you attach it and you thermocycle. And sometimes then you will bound to see failure. And with that failure is within within the not your control, but within the guideline or the spec. Nothing is perfect in this world. And then you have to present this data in a Weibull distribution data. And once you've done that, you will know whether your product at the end of the day can meet the spec or not. So you go through this simple process. You follow the instruction according to the same spec, and then you did your test, and you present data with a Weibull. And then you will quickly figure out whether you pass that or not. That's from the manufacturing perspective. Here I go a little bit deeper for the Weibull distribution for reliability. A Weibull distribution it has a unique probability density distribution. It's predicting a lifetime of product. So you have this, it is very funky but elegant the distribution functions, shape factor and scale factor. Shape factor is the most important one. And here is a lifetime of product. Here is called early life. It's called early infant mortality, which means that the product come out in a very short period of time, like that Note 7 Samsung, when they come out with a cell phone, boom, it died in a couple 3 weeks. There were a couple hundred cases of battery explosion, and that's called infant mortality. But that's one you want to avoid, right? You do a burn in, get rid of it. And then, but if you use this beta to predict it, it's better less than 1. And if the useful life, that's why you expect it can happen. And then at the end of the day, it's going to wear out. Things going to die by itself, right? Because it's too old. So all these represent a different beta. A beta equal to 1 is a flat line here. And then beta go greater than 1, you mean this. You want your product like this to be very far away like this. If this is your product lifetime, then you're dead. Your product will be had to be recalled, and you're in deep trouble. And then you don't want something that's very short. Then you lose your lifetime expectancy. Your warranty is like 1 year, 2 years, something like that. So you would like your whatever you're building your cell phone, something like to last like a couple of years, right? And then that's fine. That's fine. So this is the what the Weibo distribution is about. Weibo is a person who found this. Is a Sweden expert. It's a military colonel that actually find using this to control the military weapon output, quality control. Very nice. Very, very smart. And so this is one. If you are interested, you could come to my video, which explain pretty clear what it's trying to do.
好，我是汪部导，说半岛。今天呢，继续我们统计基础篇的第12篇。
All right, that's in Chinese. Sorry, that's the best I can do. I might turn it into English one day, but if you go to that file, you will see that you follow the pages, just the equations. It's not too big a problem. Okay. Then the last part of my talk is focused on the glass interposer patterns. I want to find out the patterns, who is doing what. And then this is a pattern I'd like to introduce you. Now, 2 patterns I found as interesting. One is one Corning. The Corning glass, obviously, they are in glass business, right? The biggest glass company. It's not a surprise they come up with a patent about glass. And they have the glass interposer patents. Now they claim that they have some kind of ion exchangeable glass that immersing this glass substrate through a bath of molten salt contains some kind of a metal ion that usually can improve the glass. Okay, that's the invention. Okay, so the glass becomes stronger, better. Okay, so that's the idea. It changed the material. And that, well, it's interesting, but not that interesting. Let's look at the interesting one, which is the TSMC one. As we introduced previously, that TSMC is the world largest packaging company for the high-end company. They are in this business. So if you look at their patterns, then usually you know what they're doing. So that's the purpose of this one. I use Perplexity AI to find out, and then I use Chat PDF to digest it. This Chat PDF help you. I already introduced this Chat PDF last time, right? Because I want to cheat. I don't want to read the whole patterns. It's very boring, and then it's so many legal jargons. It's difficult to understand. I had to spend a lot of time. But ChatGPT helped me out. But to use ChatGPT, you got to be very careful too, because sometimes the PDF you downloaded from the web is not digestible to PDF. They don't like it for some reason. They look at this PDF and say, well, doesn't fit me. Yeah, it's you, not me. And so I want to change the PDF format to another format. So I use PDF 24. This is free. You can download PDF 24 online. You convert the PDF to a new PDF. And then after that, I dump this PDF into the chatpdf.com and it worked. Okay. So pretty much you're trying to do is that it's bonding through a fusion bond. You have special fusion bonding to an interposer, the glass substrate mechanism. And then this complex structure, basically, you could improve thermal conductivity, electrical insulation, and reduce warpage. Let's try and we call this fusion bonding to another substrate. So you can have this bilayer structure, right? Like this bilayer structure. And that provide better thermal conductivity and electrical insulation at the same time. Remember, glass can do that, right? And then eventually, because the silicon substrate is so strong, it reduces the warpage. I think they put glass and silicon together for their purpose, and that's what this IP is about. And so, okay, so this is oh yeah, this guy. That's my friend. Okay, that's it. Yeah, he probably, this is one of his inventions. And so this concludes my talk, which I'm focusing on glass interposers and my fun with Perplexity AI connected papers and chat PDF. So, and I show you that for high level wise, what's it about and how can you use this tool to expand your research horizon. All right, that'll be all. Thank you.